Welcome to BKW Physics. I'm Mr. McConley, and we're going to continue our circuit discussion today. Yesterday we talked about series circuits. We talked about how the resistance is the total of all the resistors. The current is equal wherever you look in a series circuit. Voltage is the total, and Ohm's law still applies. But when you use Ohm's law, just to remind you, you have to talk about one specific location. For example, here I'm talking about location number 2. Okay, you can be talking about the totals or 1, but you can't mix 1s, 2s, 3s, and totals. You got to keep it all the same. Use that equation. So parallel circuit. What does a parallel circuit look like? Well, over here I've drawn one which we'll do as an example in just a moment. But a parallel circuit, when the electron flow emerges from the battery, it could go like this and loop around. Or it could continue on and loop around this way. Or it could continue on and take the long route. So when you have a parallel circuit, what you have is you have choices of paths that the electricity can follow. And each of these paths is called a branch. So when you have a parallel circuit, you have branches of the circuit. And it's important to keep in mind one really basic concept of parallel circuits is that the branch, I'm talking about branches, the branch with the smallest resistance, which in this picture would be this one right here because it's only 5, the branch with the smallest resistance will draw the most current. What does draw mean? Allow, yeah, attract or allow to flow through. So if you were just had an ammeter here, here, and here, 1, 2, and 3, ammeter number 1 would read the highest amount of current because it has the lowest amount of resistance. Okay? That's like a basic, if you can kind of understand that principle, it's going to help you reason through a lot of these parallel circuits a little easier. Alright, so let's get right to the rules so we can apply them to an example. Rule number 1 is a little fishy looking. It says, it doesn't say R total equals, it says 1 over R total equals. Now, you math types here, is R the same as 1 over R? Most definitely not. Don't confuse the two. These are fractions. Don't confuse the two. Okay? And I'll show you what I mean in a minute. So this would be 1 over R1 plus 1 over R2 plus 1 over R3. Yada, yada, yada. You can add as many resistors. But it's always a fraction of it. The current. Now in series circuit, they're all the same. In a parallel circuit, it does not work like that. In fact, in a parallel circuit, you add them up. Which, going back to what I said a moment ago, if this one draws the most current, and then this draws less, and this draws the least amount of current, you can see that now the current, the I over here, is getting kind of distributed between the 3 different branches. Okay? And that's why you got to add them up, because each branch gets a different amount. Unless the resistors are the same on every branch, but that's a different scenario altogether. And then the total voltage is the same. So, if this voltage is 10, how much voltage goes here? In here? In here. That's what makes parallel circuits so beautiful. The voltage is the same on any of the branches. And of course, Ohm's law still applies to a parallel circuit. Alright, let's get right to business of solving this circuit. Now, to kind of make it a little bit easier, what I've done here for you is I've listed all the things that we're going to have to eventually find. Now, some of them are given right from the get-go, like R1 is 5 ohms. So I'll just kind of fill these in. This helps me keep track and make sure I've figured out everything with the circuit. Because if I don't write this out, I start to get confused and I miss things. So R2, 15 ohms. R3, 30 ohms. And what else did they give me? Well, they gave me an I. Well, what do I call it? Well, since it's on the branch, I'll highlight it with my yellow marker here to enhance learning. See see this branch right here? The yellow branch? That's a branch in and of itself. So everything on this branch will be considered a 3. So in other words, that's definitely going to be I3. So they also gave us I3, which was 4 amps in this case. Now, what did I tell you was the best way to start these type of problems? Whenever you're solving any of these problems, what's step 1 always seems to be the best step? You remember what I told you yesterday? Total resistance. Yep. So that's what I'm going to do, because it's also one of my blanks. Now, I could start other ways. Since I have 2 of these, I could figure out what the V3 is, but just as a habit, it would be smarter, trust me, it works out better if you start with the total resistance. So here we go. I'm going to write the equation even though it's written right to my left here. I'm going to say, okay, I'm going to take resistor number 1, resistor number 2, and resistor number 3, and I'm going to add them as fractions. So I'm going to go 1 over 5, 1 over 15, 1 over 30. Now you mathematicians in here, how do you do that? Let's add them up like, you gotta get a common denominator. Oh my goodness, this is like going back old school math. So what is the common denominator with these? Okay. So we got 30, 30, 30, there's my common denominator. How many 30s is this? Everyone? How many 30s? 2. And 1. So what do I got all together? I got 9 30s. And that's 1 over our total. So is our total 9 over 30? No. No. Fractions, fractions. This is still 1 over RT. You gotta flip it. So basically, you're gonna have to take 30 over 9, right? Which is what? Let's get numbers, because we're going to need, some of these numbers won't come out. Yeah, they won't come out really even. They're going to get kind of sloppy after a while. So we got 3.3 ohms. Stop there. It seems like I messed up. Do you feel the same feeling? How can the total resistance be less than all the other resistors? Did I mess up? Or is it something about parallel circuits? It's something about parallel circuits, because you got to think of it this way. Since the electricity leaves the battery, it has 3 different ways that it can go. So there's very low resistance on parallel circuits because it has a choice. If there's a traffic jam here, where's it going? If there's a traffic jam here, where's it going? It's got 3 choices. So what happens, as you add more branches, this resistance keeps dropping lower and lower, and in fact, the total resistance is going to be less than any of the other branches individually. That's normal in a parallel circuit. If you find that in a series circuit, you screwed up. Parallel circuit, you're fine. Keep going. Okay? So, we did that. Great. Is there anything else we can figure out here? V3. Let's do V3. It seems like a nice thing to do. So V3 is I3 times R3. 4 times 30. 120. That is so much more important than you probably realize right now, unless you remember our rules of voltage, which say they're all equal. So when I found this one, which was called V3, I also found V2 what? V2? V total. Hey, that's nice. Kind of like took care of itself there, didn't it? What do we do now? We hammer them out one at a time. So we go I total is V total over R total. V total was 120 and it will be every single time, divided by 3.3. Then we're going to do 120 over 5. And we're going to do 120 over 15. What are the numbers in each case? I'm sorry, I wasn't paying attention. You got a calculator going on this? Fire them up, fire them up. All right, so we got the total one being 36.4. I rounded that a little bit because I think that's what you told me. Okay. Now, a little check before we wrap this up. Since, look back here, since the current should be the addition of all of them added up together, does it work out that way? If I take these and add them up, does it give me that? What's 24 plus 12? 36. Why is it 0.4 up? Did we round any of these?
No, it was 36. Yeah,
I rounded this one a little bit. But did I round any of these?
Well, we rounded 3.3.
That's what it is. See, we rounded this number, and then it throws up just a little bit. I was trying to figure out where we actually rounded. I knew we rounded someplace. We rounded there, and that kind of throws these up just a hair. So, yes, it's kind of like a mental check. This seems to work out well. This is everything you can find out about this parallel circuit. For today, physics.